Okay, so let us continue with our study of Fourier transforms. The first thing I want to do is to talk about a higher dimensional generalization to an arbitrary number of dimensions. Recall that we had a thing which went like, for a function f of x, we had a Fourier transform which is 1 over 2 pi integral minus infinity to infinity dk e to the power ikx f tilde of k, and the inverse transform was f tilde of k was integral dx minus infinity to infinity e to the minus ikx f of x. So these two functions formed a Fourier transform pair. Now we can do the same thing in any number of dimensions. So if you have a function of a vector r in d dimensions, say d Euclidean dimensions, then you can define 1 over 2 pi to the power d integral d dimensional volume integral over all k space e to the I k dot r f tilde of k, where f tilde of k is integral d dimensional integral over r e to the minus I k dot r f of r. So this is in d dimensions. Okay. This stands for the volume integral in k space, this for the volume integral in r space. Okay. And essentially all the theorems we prove, Parseval's theorem and so on and so forth, they all go through in this simple generalization. More interesting than this is what happens if you have a vector valued function. For instance, if you have the electric field in space or the magnetic field in space and so on, you can also write Fourier expansions for vector valued functions. So if you have, for instance, a vector field u of r, and let us do this in 3 dimensions because that is the most common example. So u of r is 1 over 2 pi cubed integral d3k e to the I k dot r u tilde, which is itself a vector of k in this fashion. Okay. So that is a Fourier expansion, and correspondingly there is an inversion formula. Okay. Now the great advantage of Fourier transforms is that just as Laplace transforms converted the operation of differentiation with respect to t to just multiplication by s, in exactly the same way the Fourier transform operation takes spatial derivatives with respect to the components of this vector r and converts them essentially to multiplication by corresponding components of k in the following sense. For instance, if you looked at the divergence of u, it would be del dot u, this is equal to 1 over 2 pi whole cube integral d3k, and then the divergence, the derivative with respect to the components of r, acts on this function here. And what is the divergence of a vector times a scalar? This vector is independent of r, so it just sits there idly, and all that happens is that it is again e to the I k dot r and then I k dot u tilde of k. So the operation of del dot is equivalent to the operation of I k dot on the Fourier component. Okay. So if you take the divergence of a vector in 3 dimensional space, that corresponds to taking the dot product with I k on the Fourier component u tilde of k. In exactly the same way, del cross u of r, these are all functions of r, is 1 over 2 pi whole cubed integral d3k, again e to the I k dot r. You need the formula for the cross, the curl of a vector times a scalar, and the vector in this case does not involve r at all, so you just have one term, and that is I k cross u tilde of k. So the dot product with del is converted to I k dot, and the cross product is converted to I k cross. This means that these operations, these partial derivative operations, are converted to algebraic operations. taking scalar products, dot or cross products with this vector ik out here. Now of course, as you know, in Maxwell's equations for example, that is a set of equations in which the spatial derivatives are always either curls or divergences of the vector fields, the E and B fields, and if you Fourier transform them, then Maxwell's equations get converted to a bunch of algebraic equations for the Fourier transform. Of course, you also have partial derivatives with respect to time, and therefore you do a Fourier transform with respect to time, and the conjugate is the frequency omega. So derivative with respect to t becomes just multiplication by I omega or minus I omega depending on the convention. Okay. So you can convert Maxwell's equations to a bunch of algebraic equations for the Fourier components, and then of course once you solve for that you can invert the transform in principle to get the original fields. Okay. So it is extremely useful. Now tell me, why is it, just to recall to you, why is it that the differential equations of physics, like those in fluid dynamics for instance or in electromagnetism, why do they specify the divergence and curl of a vector field? Why not some other derivatives? After all, if you have a vector field u and it has got components u1, u2, u3 say, and del has components delta over delta x, delta over delta y, etc., you have 9 possible derivatives, but the only ones that seem to play a role are the curl and the divergence. So if you wrote these derivatives down, if you wrote del I uj, this stands for delta over delta xi where I runs 1, 2, 3. This is a second rank tensor, it has got 9 components, and the divergence is just the sum of the diagonal components, and the curl is just the set of 3 numbers formed by taking the differences of the antisymmetric components. Why do those two play such a fundamental role? What is the reason? What do you think is the reason?
Specifies that if the curl and the divergence of a vector is given,
yes,
and provided it is well behaved on infinity,
yes,
then you can find out that.
You can find it uniquely, yeah. This is called Hemolysis Theorem. It essentially says that if in a region you specify the divergence and curl of a vector field and you specify the normal component of the curl on the boundary surface, then the field is uniquely determined by these. Now of course there is one more physical reason why the divergence and curl play a special role, because they have specific transformation properties. This is a second rank tensor here, this thing here, but the divergence is the trace of this matrix and is therefore invariant under rotations. It is a scalar, transforms like a scalar. On the other hand, the curl, as you know, transforms like a vector. So these combinations have well defined transformation properties, and that is crucial in what happens. So in fact what you normally do, if you recall, if you look at the multipole expansion for the potential due to an arbitrary charge distribution for instance, then you have a monopole term which is a scalar, you have a dipole term which is a vector, and then you have a quadrupole term which is a tensor of rank 2, but a very special tensor of rank 2. It does not have 9 components, but it has 5 components. The reason is it is a symmetric tensor, so it only has 6 independent components, and then it is traceless because you get rid of the scalar part, which is the trace of this tensor is a scalar. You get rid of it, it is already gone in the monopole term, you subtract it out and then you are left with 5 and so on. So what happens in general of course is that if you have a tensor of some rank r, then you have 3 to the r components in 3-dimensional space, but then when you convert it you remove all the lower dimensional representations of the rotation group, and then of course you get spherical tensors, and a spherical tensor of rank r has 2r plus 1 components. So 3 to the power r gets converted to 2r. In the case of the quadrupole, 9 components gets converted to 5. In the next stage it will be 21 components for the next multipole moment, but it gets removed, the earlier ones are all subtracted out, and then you end up with 7 of them and so on. Okay. So to get back to where we were, the divergence and curl play a very special role because of this theorem, and we see here that once you have this function e to the ik dot r acts like some kind of eigenfunction for the del operator, and del dot becomes ik dot, del cross becomes ik cross, and therefore life becomes extremely simple once you Fourier transform. Okay. Now let us now change topics and go on to a very, very important formula in Fourier analysis, and this is the Poisson summation formula. We are going to derive this formula in its simplest form, a very, very elementary form, but it is a very profound result and it has very deep implications in many branches of mathematics, but we are not going to do the complicated parts of it. We are going to see what this formula does for you, and it does something fairly non-trivial. Okay. In some sense what it does has already been seen by us when we looked at the Fourier transform of a Gaussian. You recall that if you have a Gaussian function f of x was e to the minus x squared over 2 sigma squared, say 0 mean just to be simple, divided by 2 pi sigma squared, a Gaussian centered about the origin, then the width of this Gaussian, the full width at half maximum for instance, is proportional to sigma squared. Okay. The larger sigma squared is, the wider this Gaussian is, and the narrower it is, the smaller sigma squared is, the steeper, the sharper the Gaussian is. On the other hand, this thing implied that f tilde of k was equal to e to the minus k squared sigma squared over 2. So a very broad width in x space led to a very small width in k space and vice versa. So if sigma is very large, this thing here sits here in the numerator as opposed to the denominator and just does just the opposite. Okay. We saw this in terms of the uncertainty principle, for instance. I said that if you have a wave packet in x space for the position of a particle and that is very broad, then you expect in momentum space the distribution is rather sharp, and so on, and vice versa. Okay. Now the Poisson summation formula generalizes this and shows you precisely where this relation comes from. In fact, it's this case is so important that this is occasionally called the Poisson summation formula, but in the sense of a summation which I am going to talk about, but this is not it, it is a more general formula. Okay. So we start with the following. Let us start with the function of x, which is just a sum of delta functions, okay, periodic array of delta functions. So the summation n equal to minus infinity to infinity delta of x minus n times L, where L is some length scale, some constant, positive constant. Okay. Now what does this function look like? It is just an array of delta functions. So as a function of x, there is one at the origin, there is one at L, there is one at 2L, there is one at minus L, minus 2L, and so on. It is just an array of delta functions. It is sometimes called the Dirac comb. Okay. Looks like a comb, and it is just a bunch of Dirac delta functions. Okay. Now we could regard this as a periodic function with a fundamental period that lies between minus L over 2 and plus L over 2. And this delta function is repeated with a period L. Okay. And the fundamental interval is minus L over 2 to plus L over 2, say. Then of course I can also write this same f of x as equal to 1 over L summation over n equal to minus infinity to infinity f sub n e to the 2 pi ni x over L. Could write it in a Fourier series. Okay. And the period is L. Right, here. So that is the Fourier series expansion of this periodic function, which is just an array of delta functions. Okay. This immediately implies that the inversion f sub n is equal to an integral from minus L over 2 to L over 2 dx e to the minus 2 pi ni x times f of x, x over L. That is the inversion formula for the Fourier coefficients of this function f of x. Okay. but in this range this f of x is a single delta function at the origin. So this guy here is essentially delta of x, that is the only one which contributes in the fundamental period, okay, and that will immediately of course give you 1. You put in this delta function and do the integral, then you set x equal to 0 and that is it, it is equal to 1. Okay. So going back here, this says that f of x equal to summation over n. If I do not write limits, it means from minus infinity to infinity, just for short, delta of x minus nl is also equal to 1 over L summation over n e to the 2 pi ni x over n. Okay. I would like to get rid of this 1 over L, so let us write this as equal to, take out the L, so there is a 1 over L summation over n delta of n minus x over L, because recall that the delta function is a symmetric function of its argument, delta of minus x is same as delta of x. So this gives us a very, very interesting result. It says a summation over delta functions of the form n minus x over L over n is the same as a summation over n of exponentials. Okay. So sum of these exponentials is equal to this. And of course you could ask, how is this going to happen? These delta functions are all extremely sharp. The answer is, of course, there is destructive interference between these different cosines and sines, so that they cancel each other and give you essentially peaks of this kind. Okay. So that is the first part, first result that we need. Now let us do the following. Let us go back here and say, look, I am going to regard this function f of x as defined from minus infinity to infinity, and let us do its Fourier transform. Then what do I get? F tilde of k equal to a summation is equal to an integral minus infinity to infinity dx e to the minus I k x times the summation over n delta of x minus n L, and this is equal to a summation over n, and I pick up the contribution from the delta functions everywhere. So it is equal to e to the minus I k n L. Okay. But since this sum is from minus infinity to infinity, I can change n to minus n and the sum does not change. So this is also equal to summation over n e to the I k n L, just by changing n to minus n, does not change the summation. And now I would like to use this formula, I would like to use this. So what I do is to write this as equal to a summation over n e to the 2 pi I, so let me write this so that it is transparent, 2 pi I n x over L. So e to the 2 pi I, and then there is an n x over L, and that becomes delta of n minus x over L here. So let us do the same thing here. You have 2 pi I n k L over 2 pi. And that is exactly of this form. So this becomes equal to, where does it go? It is equal to summation over n, a delta function of n minus k L over 2 pi. So if f of x is this array of delta functions, its Fourier integral, Fourier transform, is also an array of delta functions of this kind here. Okay. And now we go back and look at the generalization of Parseval's theorem that we already deduced. Okay. And what that result said was the following. It said that if you have two functions f of x and capital F of x, then the integral from minus infinity to infinity dx was equal to 1 over 2 pi integral minus infinity to infinity in k space f tilde of k f tilde of k. Okay. That was the generalization of Parseval's theorem, and if you recall, I said if you set this f of minus x, capital F of minus x, equal to f star of this function, then you got Parseval's theorem, which said that mod little f of x whole squared integrated is equal to 1 over 2 pi mod f tilde of k whole squared. Okay. That is, the norms were essentially equated in the k basis and the x basis. But this is a generalization of that result, and now what I am going to do is to substitute in this equation here. I am going to substitute for f of x from here, and I am going to substitute for f tilde of k from here. This thing here. F of x is this delta function array, and incidentally notice also that in this instance f of x equal to summation over n delta of x minus n L, it is also equal to f of minus x, because all I have to do is to change n to minus n. Once I put minus x here, I change n to minus n, and then I am back to the original formula. So it is again symmetric, and as we saw, it is an array symmetrically distributed about x equal to 0 on both sides. So if I plug that in, this immediately says summation over n f of, now x is replaced by nl, so nl, this thing here, is equal to 1 over 2 pi integral minus infinity to infinity dk f tilde of k, and then summation over n, and this thing here delta of n minus kl over 2 pi, and I would like to do the k integration. So I need a delta of k minus something or the other to do that, and that is easily obtained, because I can also write this as delta of kl over 2 pi minus n, and I can take out this constant L over 2 pi. Now what is delta of Ax equal to, where A is a constant? 1 over mod A times this, in this case A is L over 2 pi, so this becomes 2 pi over L, and then there is a 1 over 2 pi summation over n, and I pick this up, so there is summation over n f tilde of 2 pi n over n. So we have our final result, which is the Poisson summation formula, and it says that if f of x is a nice function, then summation over n f of n L, where n is L is any arbitrary positive constant, this is guaranteed to be equal to 1 over L summation over n, and now let us write this out, minus infinity to infinity f tilde this is the famous Poisson summation formula. So it says if you sample a function at all the integers, some integer multiples of some constant L, you get the same thing as what you get if you sample its Fourier transform at integer multiples of 2 pi over L. So if L of course is very large, then the sampling in k space has to be very small. You have to sample very much more frequently. Okay. So notice this is the crucial point, that L appears in the numerator here and it appears in the denominator here, in this conjugate fashion, if you like. So this entire business with delta functions and so on was an artifact. I put L as an arbitrary positive number. For any positive number this is true, this relation, and that is the famous, this is the summation formula in this instance. Let us apply it now to the case of the Gaussian which is what I said I would do. And in the case of the Gaussian, I know what f tilde is. So I know that f of x equal to e to the minus x squared over 2 sigma squared over square root of 2 pi sigma squared. So that is an example. This implies that f tilde of k is e to the minus k squared sigma squared over 2. And let us put that in, and then you get this very remarkable formula which says summation n equal to minus infinity to infinity e to the power minus, instead of x you put n, so it is n squared L squared over 2 sigma squared over square root of 2 pi sigma squared. This is guaranteed to be equal to 1 over L minus infinity to infinity e to the power minus, instead of k you have 4 pi squared n squared over L squared sigma squared over 2. So let us move this up here, and you have equal to root 2 pi sigma squared over L. There are too many constants here. There is L and sigma. We can combine these guys. So let us combine them in the following way. Let us put L over root 2 pi sigma squared equal to lambda, say, and then what does this give you? L squared over 2 sigma squared is pi lambda squared. So summation n equal to minus infinity to infinity e to the minus pi lambda squared n squared, and that side is equal to 1 over lambda summation n equal to minus infinity to infinity e to the power minus is a pi, and then 2 pi sigma squared L squared n squared over lambda squared. Okay, lambda positive. So this is an extremely remarkable formula, because it is saying something about a sum over the integers of not e to the n, it is not linear in n, but it is quadratic in n. Such sums are called Gaussian sums, and they have a large number of weird intricate properties, and the whole theory of theta functions and so on involves such sums. Now notice what has happened. It says a sum over such exponentials e to the minus pi lambda squared n squared is equal to, the lambda appears in the denominator here, okay, and it is an identity. This identity, by the way, is due to Jacobi. And it is so important that it is sometimes called the Poisson summation formula itself, but actually the summation formula is this, and that is a special case of it here. Now lots of implications here. In physical problems you might end up with lambda as a parameter, and you would like to study its small lambda behavior, large lambda behavior, and so on, and now these two things will give you complementary views of the same thing. For instance, in the diffusion problem, which we will talk about a little later, this lambda will turn out to be proportional to the time itself in a diffusion problem, okay, turn out to be the diffusion constant times t, little t. Then we would like to see what the solution of a diffusion equation does for small values of time and for large value, very long times, and this identity here will give us a handle on that. This will tell us which formula is better at small times and at long times. It is clear that if lambda is very large, this dies down as n increases, so you could approximate it with the first few terms, and if lambda is small, then you would do the same approximation on that side there, okay, and they are different representations altogether. Okay. Now one can play this game with any function. So we already looked at one more example of a probability distribution, and that was a Cauchy distribution. Let us see what it says in that case. So in the case of the Cauchy distribution, my f of x was equal to some lambda over pi times x squared plus lambda squared. Okay. Let us not, there are too many lambdas appearing, so let me call this a for the moment. Okay. Some x squared plus a squared. And what was the Fourier transform of this function? F tilde of k was equal to, this is a normalized probability density, normalized to unity from minus infinity to infinity, and it behaved like this. This thing was some bell shaped curve of this kind where this width was proportional to a, and f tilde of k in this case was e to the minus lambda modulus k, a modulus k. It is a characteristic function being the Fourier transform of a probability density, so f tilde of 0 must be equal to 1 for normalization. That is indeed true. And what does this function look like? It is exponentially damped and it has got a little cusp at the origin, k space. So let us plug that in there. Let us put that, let us put n equal to 1 for instance, and then this says a over pi summation n equal to minus infinity to infinity f of n, so that is 1 over n squared plus a squared. Recall we had already found the sum here. This gave you the Langevin function, it was pi over 2a cot hyperbolic pi a minus 1 over pi a or something like that. So here is another way of doing it, and that is to use the Poisson summation formula, and this was equal to summation n equal to minus infinity to infinity f tilde of 2 pi n, in this case e to the minus 2 pi a modulus n. We could simplify that. We need to simplify this, so this is equal to, so let us take the term which is n equal to 0, that is just a 1, plus twice a summation n equal to 1 to infinity, case, e to the minus 2 pi a n. What is this equal to? A is some positive number. What is that equal to? That is a geometric series, so it is trivial to sum, and this is equal to 1 plus 2 times e to the minus 2 pi a over 1 minus e to the minus 2 pi a, right. So that gives you a 1, so that is equal to 1 plus e to the minus 2 pi a over 1 minus e to the minus 2 pi a, multiply numerator and denominator by e to the pi a, and this gives you cot hyperbolic pi a. So we are back to this result we already know, which essentially says that summation n equal to minus infinity to infinity 1 over n squared plus a squared is equal to pi over a cot hyperbolic pi a. And now of course what you should do is to separate out the n equal to 0 term and rewrite this. So you can rewrite this also as equal to 1 over a squared plus twice summation n equal to 1 to infinity 1 over n squared plus a squared equal to that, and then you get the usual expression for this sum. And if you recall, in this sum, if I set a equal to 0, what do I get? You get the zeta function for 2, argument 2, so you get pi squared over 6 and so on. You can do this a little more generally. You could actually start with the f of x, and I will leave that as an exercise to you. Start with f of x equal to some cos bx over x squared plus a squared. This whole thing is for b equal to 0, but you can do the same thing with cos bx here. What you have to do is to find its Fourier transform, and when you do that, write this as e to the I bx plus e to the minus I bx over 2, combine it with the k, and then you get, once again, you get Lorentzians whose Fourier transforms you already know. Okay. So I leave this as an exercise, a little generalization of this formula. Okay. Now once again, as you would expect, this summation formula also is generalizable to higher dimensions. You can do this in any number of dimensions. So these things here, this n, instead of that you have r tuples of numbers of integers, and you can now do Fourier transforms in higher dimensions and do an analog of this summation formula here. And there are further generalizations. So there are lots and lots of very interesting results which start with this very elementary Poisson summation formula and then go on to fairly intricate things about the heat kernel, its asymptotic behavior and so on. We will come back to the use of this formula when we solve the diffusion equation, which we are going to write down the fundamental green function for the diffusion equation, and when we do that we will see the use of this, the actual practical use of this formula. In addition, of course, to the fact that when you have a relation like this, it is useful for summation of series, because there are cases when you can sum this, and this is harder to do. In this instance, for example, this side here was just a geometric series, whereas this side here was much more complicated here. On the other hand, you see immediately how this formula immediately helps you to find one of the left hand side given the right hand side. Sometimes it happens the other way. In the Gaussian it is equal on both sides, they are both Gaussian sums, and what we have done is to show that two Gaussian sums are equal in this specific form. Okay. Many other things, you can amuse yourselves by doing this for various other probability distributions. In this case you can see what happens to this formula. Okay, so this is about all I wanted to say about Fourier transforms. We will return to the use of Fourier transforms when we do scattering theory. We are going to talk about integral equations, and at that time we will come back to this to some of these formulas here and use them in this.